So far, we have learned that geometrical isomerisms are shown by the restricted rotating systems, and these are the examples of the restricted rotating systems. We have also learned two simple rules to identify the geometrical isomerisms in alkenes, cumulated dienes, and Spiro compounds. So two rules which we have learned are applicable to all these three systems. Now we are going to see the geometrical isomerisms in triphenyls systems, cyclic compounds, compounds containing carbon double bond nitrogen, and azo compounds. Geometrical isomerism in triphenyl system. Before moving to triphenyl systems, let's understand what are biphenyl systems. When two aryl rings connected with carbon-carbon single bond, then it is known as biphenyl system. This is the example of the biphenyl system, where two benzene rings are connected by a single bond and there is a free rotation around this carbon-carbon bond. So this molecule can be converted into in this way, where one benzene ring is perpendicular to the second benzene ring. So if this benzene ring is in the horizontal plane, then this will be in the vertical plane, and hence you can divide this molecule easily by passing horizontal plane, because there is no substitution on the benzene ring. So it can be divided into identical half. So such molecules has plane of symmetry. So when the molecule has plane of symmetry, then it means there will be no optical isomerism. Now we have to also understand that this energy barrier of rotation is very less, and therefore you can see this equilibrium at the room temperature, and these two isomers, number A and B, are known as Atropisomers. So these Atropisomers are in equilibrium with each other. Okay, to see the geometrical isomerisms, the systems must have to follow two rules. Rule number 1, each rings must be attached to two different bulky groups. Rule number 2, both groups must be in the same plane. If you remember, these rules are same which we have learned for alkenes, cumulated dienes, and Spiro compound. Now if we want to restrict the rotation around this bond, we need to put some bulky group at ortho position. So you have to put the bulky group at the ortho position, some bulky group, so that it can hinder the rotation around this carbon-carbon single bond. And similarly, this ring must have bulky group as well to stop this rotation. Once you stop this rotation, then this ring is in perpendicular, or this ring in the vertical plane get locked, and hence you can't give the further rotation. Therefore this molecule will have no plane of symmetry, because if you pass this horizontal plane and this part is in the vertical plane, you can't divide into equal half, because there is a hydrogen and there is a bulky group. Therefore this compound has no plane of symmetry, and it will show you optical isomerism, and such compounds are chiral due to axis of chirality. This is called axis of chirality. I forgot to tell you, alkenes also have chirality due to axis of chirality. What does it mean? So let's look other example. Let's say you have this kind of compounds where one ring have methyl and carboxylic group, and the other ring also have different substituents. One is carboxylic, another is methyl. So due to the presence of this bulky group at ortho position, this rotation is not possible. So the system will get locked at this position, where this ring or this ring could be, one of the ring will be in horizontal plane and another ring will be in vertical plane. Let's say the first ring is in the vertical plane and another ring in the horizontal plane. So due to which, if you pass the horizontal plane through this molecule, then you can't divide this molecule into identical half. So this compound doesn't have plane of symmetry, and hence it will show the optical isomerism. So it will show the optical isomerism, and as I told you, this types of chirality is known as axis of chirality. What does it mean? It means that this axis which is passing through the molecule, this axis, around this axis all these four groups, these 1, 2, 3, 4, have tetrahedral environment. And we learned that in the previous part that due to tetrahedral environment, it will never show geometrical isomerism, but it can show the optical isomerism if it has different substituents on the each ring. So here it is satisfying the rule number 1. It is not satisfying the rule number 2, which is saying that both groups must be in the same plane, because this group is in vertical, this is in horizontal, and it has tetrahedral environment. So no geometrical isomerism, only optical isomerism. Remember this trick. First ring is in the vertical plane, another ring is in the horizontal plane. So both rings are not in the same plane, and hence this is called tetrahedral environment. And in case of tetrahedral environment, you don't see geometrical isomerism. No geometrical isomerism. Only optical isomerism is possible. Optical isomerism is possible because there is no plane of symmetry. If you put methyl at this part and methyl at this part, then this compound will have plane of symmetry, because this horizontal plane then can divide into two identical halves. So therefore it must be different. Now let's look at the triphenyl systems. In case of triphenyl systems, let's apply the simplest way. First ring is in the vertical plane, so next will be in horizontal plane, and next will be in vertical plane. So alternatively vertical, horizontal, vertical. So now you can see that the terminal part is in the same plane. What does it mean? It means that it has square planar environment, and we have already learned about the square planar environment. When you have square planar environment, this implies that it will show geometrical isomerism. It will show geometrical isomerism. But these types of molecules have plane of symmetry and hence do not show optical isomerism. So triphenyl systems will show only geometrical isomerism. So this one will be trans, because if you see this carboxylic group, it is opposite from this carboxylic group, and this methyl is opposite to this one. And what will be the cis form? So for the cis one, you can draw. So put methyl on the same side, and here you don't need to change anything. So this will be cis isomer. So it has only total stereoisomers 2.